So yeah, I work about 3 miles north of here in Columbus, and I'm an assistant professor in civil engineering as well as agricultural engineering. I'm kind of split strangely across those two departments. And I'm going to talk to you today about, again, some ODOT-funded research. It'll follow on very nicely to the last speaker, and you'll see that the question I posed, we'll go into some of the data, the reason why I posed that question about trash in just a few minutes. So what we were doing here is a field study to look at both particle size distribution as well as the trash component of the total solids loading coming off of typical ODOT maintained roadways. And you'll see that we did that across this lovely state. So a quick outline, just a bit of background, motivation for the project, the reason why we were undertaking this research, the problem definition, we'll talk about the monitoring design in some detail, and then also obviously the results and hopefully some take-home points that you can take back to your state and your DOT. So a little bit of background, obviously, stormwater causes a lot of problems. We have issues with both flooding as well as nutrient loading, as you can see here in Lake Erie, specifically here in Ohio. So there's a whole lot of different pollutants that are carried by stormwater. The ones we're really interested in this particular talk are sediment, or TSS, and then the trash portion of that total solids loading. So really the entire portion of the solids loading coming off of the roads. So road runoff is recognized as one source of non-point source contamination to waterways. There's a lot of highway-specific issues. So we've got abrasion of vehicular components, right? That's where a lot of our metals come from, brake wear, tire wear, et cetera. Atmospheric deposition of things like nutrients, and then just wear of the wearing course of the actual road or bridge in the case of what I'm showing here. So some of the pollutants of concern, sediment's probably the most common across the country, right? We typically analyze this as TSS, and it's just a lumped number of everything less than 2 millimeters, essentially, right? We get back 35 milligrams per liter or 200 milligrams per liter from the lab. We don't really have any understanding of, is that clay, is it silt, is it sand, is it easy to remove, is it hard to remove? We have no idea, right? We're just getting one lumped number back from the lab. The trash side of things, or what I'm going to call gross solids, and the reason we do that as engineers is we can charge more to reduce or take away gross solids out of stormwater than we can for trash, right? Trash sounds really easy to take care of. Gross solids sounds really hard, right? So we can charge more for it. Typically, these are greater than 1/4 inch in diameter. They're not picked up by our auto samplers that we'll typically use for stormwater research. And there are some TMDLs out there for trash. And they're really hard to meet, right? They're doing a lot of catch basin inserts. I think San Francisco has like 20,000 catch basin inserts. The level of maintenance required is shocking, as the last speaker talked about. And so it just gives you an idea here, just a quick picture of the types of solids. So we go all the way from the colloids at the very, very smallest ends up to the trash right on the big ends, the Coke bottles, the diapers, whatever you find in all sorts of good things like dead birds that we found in stormwater and some of our analysis. My undergrads really enjoyed the smell of those after they came out of the freezer. But for ODOT, the real importance here is compliance, right? They're trying to meet that 80% TSS removal that the last speaker talked about for post-construction stormwater management. And in this case, we're really interested in manufactured treatment systems, right? These manufactured devices that you can plop in the ground along an I-71 or an I-670 corridor where you don't have a lot of right-of-way, and where you don't have that right-of-way, you potentially have to acquire it as one of the previous speakers from Florida talked about. You're spending tons and tons of money on acquiring that right-of-way. And so can we basically use these manufactured treatment systems to reduce sediment to the point of 80% TSS removal? Generally, these systems capture particles greater than 75 micrometers well, okay? And I'll talk a little bit about that later, but keep that number in mind as we go through some of the data. So currently, ODOT has 21 different qualified products. They're manufactured by different companies, private sector companies across the country. They're all hydrodynamic separators at this point. For those of you who aren't familiar, this is the type of treatment system that a hydrodynamic separator is. It's basically a large cylindrical tank that gets put in the ground. The stormwater comes in through basically a centrifugal force type of situation. The sediment and a lot of the trash is accumulated in the bottom. Then the stormwater goes up and out through the outlet into the storm sewer network. And then you come in periodically, typically once a quarter, and suck all that out with a vac truck. Okay, so that's the maintenance that's involved, relatively simple maintenance. As the last speaker nicely introduced, I really don't have to talk about this slide. There's two different methods, or there's actually a number of different methods, but two main different methods that are out there for evaluation of these manufactured treatment devices. It's typically done in the lab, and so you can use either the OK110 distribution, which is this very, very sandy distribution that ODOT currently uses, Or what's being used a lot more frequently across the country is this NJDEP or TARP distribution that has a lot more clays and therefore is much more difficult to get to that 80% threshold, okay? So our basic question here, so just to give you an idea, to get 80% TSS removal for the OK110 distribution, you really have to remove all the particles greater than 90 micrometers. Relatively easy to do, okay? If you do that same thing with the NJDEP or the TARP distribution, you have to get down to 9 micrometers. So you're down very, very low, very small silt size fraction. So it's much more difficult to hit. So the question really in this project was, does the stormwater look like the OK110 distribution, or does it look more like the TARP distribution? Okay, that's the basic question we're going to try to answer. The reason why this question is important is it ties into stormwater control measure design, ties back to the hydraulic retention time that you need within these practices in order to get to that 80% TSS removal, okay? So if you have very, very sandy particle size distribution, you might need on the order of seconds to minutes of hydraulic retention time in order to get to that 80% TSS removal. If you have very clay, you might be on the order of many hours or many days worth of retention time, or you need to go to some sort of filtration-based practice to get to 80% TSS removal. So really what we're trying to do is analyze across the state different pavement types, different roads across the state where we went out and did field monitoring to understand differences in particle size distribution. We also looked at TSS at these road sites and tried to tease out what are the causal factors in the particle size distributions that we're seeing. And then also collect gross solids or trash from the road runoff and look at how much of that is coming off so we can characterize the entire suite of the total solids essentially coming off of the road. So we did this at 12 different sites across Ohio. You can see those in yellow here. They're kind of spread across every region of Ohio except for Southeast Ohio. Sorry to those of y'all from Athens that are in the room. But everywhere else really is quite well represented, as you can see in this figure. The design basically was we did 6 sites in 2016, 6 in 2017 across a range of different types of roads, so primary routes, interstate highways, et cetera, asphalt wearing course, concrete wearing course, et cetera. We collected runoff proportional samples using ISCO samplers and measured rainfall at each site on a 1-minute interval. And you can see some of the sites here that we monitored. Some were in the city, some were in rural areas. We really tried to hit the gamut of different roads. We basically measured flow, as I'll show you in just a second, within each catch basin using a weir and a pressure transducer, and then triggered samples using the automated samplers I just talked about. We were very careful to isolate roadway drainage only, so we were not bringing on runoff from a Walmart that was adjacent. We were very careful to just make sure this was ODOT maintained right-of-way. And again, we looked at a variety of road characteristics, which I think I beat that horse dead quite a while ago. And as part of the literature review, we looked at a number of studies that have been done over the last basically 20, 25 years on particle size distribution. And one of the interesting findings that we found with each of these dots representing a different study done by a different research group is that the type of sampling you do really affected the median particle diameter coming off of the road. So if you went in with a vacuum truck and you vacuumed up all the sediment, not surprisingly, you have a really large median particle size of about 250 micrometers, or well into the sand size fraction. That's because you're picking up everything, right? Those particles aren't necessarily going to be entrained in the stormwater the next time it rains, right? So there's a big difference there in how you sample. So we really struck that as our sampling method quite early. Grab and time-paced sampling and flow-paced sampling resulted in relatively similar median concentrations. We ended up doing flow-paced sampling, but you can see those are the past median concentrations are somewhere between 40 and 80. We'll keep that in mind as we move forward to our results here. This is a typical catch basin, the type of equipment that we installed in the catch basin. We're basically forcing all the water coming off the road behind this weir, and then we measure the flow rate over the weir using a pressure transducer, and then pull our samples through a tube back up to a sampler that's located up near the road. And then we bring them back to the lab. So we sampled 176 storms across the 2 years, across the 12 sites. So 12 to 18 storms per monitoring site, pretty good, robust data set. We run them through basically a laser diffraction particle counter, which is a fancy $80,000 machine that can measure basically the particle size within that sample. And it reports everything from basically small colloids up to the largest of the sand size fraction, okay? So what did we find? So here's, again, the same slide I showed you earlier of the 2 different testing distributions that are typically used. What we found on average is the orange the orange distribution that you see there. So it really mirrored quite well the New Jersey or the TARP distribution, except for the area between about the 10th percentile and the 40th percentile, where it was slightly more sandy or larger particle sizes than the New Jersey distribution. Otherwise, it mirrored the New Jersey distribution quite well. The D50 was about 66 micrometers. The D20 was about 25 micrometers. So if you're doing the math and you're trying to get 80% TSS removal, you'd have to remove everything larger than that 25 micrometer number, which is actually quite challenging. And you can see I'm just putting up here clay, silt, and sand, so you get a frame of reference for the fact that there was actually not a lot of clay in what we found in the field monitoring. The majority was silt and sand, which is good for BMPs, right? It's going to be easier to drop out, easier to allow to settle out. Just to give you an idea of the variability, this is all 176 PSDs in one figure. So this is, there's like 200 bins of particle size here. And you can see that there's a lot of variability. These are separate box plots. Each one of these are separate box plots. And this black line through the middle is the median value that I showed you on the last slide, the orange line that I showed you on the last slide, or the orange distribution I showed you on the last slide. And you can see there's a huge level of variability. So really picking a particle size distribution, if I were to tell you, I would just go with the New Jersey distribution here, because there's so much variability around the median that it would be hard to take one of our data sets and say, yeah, this is the exact one that I would use for testing. Okay, in terms of particle size distribution, these are the sites here along the top row, percent sand, percent silt, and percent clay. I just want to highlight that really the sand was, in general, the majority of the particles that were coming off the road. This is nice because you can really have a short hydraulic retention time. Something like a vegetated filter strip, a swale, are going to drop out all of those sand-sized particles, or the vast majority of those sand-sized particles. The silts, right, you're now getting into a moderate hydraulic retention time where you might need 30 minutes to many hours worth of retention time within a BMP in order to take care of those. And then clays, you're really getting to filtration mechanisms, right? We're getting away entirely from the swales and filter strips and the easy BMPs to install in the linear right-of-way. In terms of TSS treatment efficiency, this is just some data that from a previous study. You can kind of look at the different BMPs here: hydrodynamic separator, dry detention basin, pond, and wetland. You get the idea that the hydrodynamic separators, for the smallest particle sizes, they're really not providing any removal at all. And again, our median was right in the 60s for particle size, so you get the idea that this might not be the best treatment practice. For systems that have longer retention times, we're certainly going to see greater treatment and even treatment of some of those clay-sized particles or the less than 2 micrometer sized particles for a pond, in this case up in Toronto. One of the other things that we found that was interesting is the TSS concentrations coming off the roads were actually much smaller than what the last speaker talked about. The average concentration that we saw was 35 milligrams per liter. So it was very clean water. So those of you who deal with percent removals versus effluent concentrations, getting 80% TSS removal when your influent concentration is 35 milligrams per liter is a big ask, folks. That means you got to hit like 7 or 8 milligrams per liter as an effluent concentration. That's really tough. You're at some sort of filtration practice, if not a treatment train, to get there at that point. Okay, so those of you who work with regulators, that's something to think about. I'm not a fan of percent removal. Wearing course did have an effect. The largest particle sizes were actually different between concrete and asphalt. So we had statistically significant differences in D90 with larger D90s for concrete than for asphalt. If you ask me why, I will tell you I have no idea. That's just what we found in the field data. I have no clue why. I'd be interested to have some discussions around that if anyone has any ideas as to why that might be. In terms of functional class, interstate, principal arterial, minor arterial shown here, you can see there was, if you just visually look at that, you're like, yeah, those are all the same. And in fact, statistically, they were all the same. So there was no difference in PSD across different functional classes of roads. So findings, PSDs are really highly variable. That's probably not a surprise to those of you who have done some data collection in this area. I'm not a fan of percent removal. I'm just going to leave that slide at that and talk about the gross solids side of the study. So what we did was we, again, instrumented at 11 sites, in this case, not 12 like the previous part of the study. Basically installed purpose-built mesh netting, which it was basically a catch basin insert that we had built with 1/4-inch openings, and they basically dropped down into the catch basin as essentially an insert. And then we installed a 2x4 flow diverter to get the water out of the gutter pan and out into the actual graded part of the catch basin. We didn't want it to go through the throat and basically bypass our insert. So we wanted to make sure, as the last speaker did, that all of the water was being filtered. So that's one drawback of these data, is that in reality, some of the water is going to go through the throat, and that trash is, of course, going to bypass any treatment. Okay, so just keep that in mind. We visited the sites every 9 to 12 days to collect the samples, and my students were diligent in basically bagging these huge amounts of basically trash and debris and leaf litter and everything that comes off of a road over a typical year, okay? Took them to the lab and analyzed for wet weight. We actually did some dry weight analysis as well, and also measured volume of each sample. And we did that. My students literally sat there with tweezers and separated out all of these different parts of the gross solids that come off of. So y'all are really thankful that you don't work for me right now, right? Now they were actually good sports about it. But you can see the different sort of bins of data that we collected here, and these are some of the samples here. People in Ohio, I guess, smoke a lot. There's a lot of cigarette butts, surprisingly. But here's an idea of the sample wet weight per catch basin. So this is thinking now about how do we maintain this. We're going out with a vac truck, so how many vac trucks do we need, that kind of thing. So knowing the wet weight could tell you that kind of information. And you can see there's a high level variability. The median per pounds per catch basin over, again, a 9 to 12 day interval was generally less than 1 pound. We had one site along I-70, which is a hugely traveled corridor here in Columbus, that had much, much higher trash loadings than any other. And you can see the maximum trash loading over a 9-day period was 62 pounds. So that's a lot of trash, right? And so that would completely clog any catch basin insert on the market in a week, essentially, at that particular site. Again, that was only 1 week out of an entire year of monitoring, so keep that in mind. If we then extrapolate quite a bit to a pounds per acre per year or pounds per acre per day type of basis, you can see median pounds per acre per day, taking into account the watershed area to each of these catch basin inserts, is really somewhere between 0.1 and 0.5 pounds per acre per day. And so you can start doing that math and figuring out what fraction of the total solids this represents. In terms of composition, what we found, what was the majority of the gross solids coming off the roads? Really, the vast majority at all of the sites was natural vegetation. So it was essentially either leaves during the fall or typically grass clippings following mowing occurrences. So oftentimes there was very, very little volume of gross solids, excepting periods where there was maintenance, i.e. mowing, or leaf fall in the autumn, okay? The other thing that we found that was substantial in a lot of places was rock or aggregate, small, basically pieces of asphalt that had broken off, were larger than the TSS or larger than the tubing for our sample intakes for the particle size distribution, but were larger than a 1/4 inch, basically, so they were captured in our catch basin inserts. So rock and gravel was a big one. Plastic, not surprisingly, plastic bottles was another one in terms of wet weight. That played a big role in the total weight measured over each year at each of the sites. In terms of volume of each of the types of trash, again, natural vegetation, grass clippings, leaves was the biggest part. So anthropogenic litter was a relatively small portion, say 10 to 20 or 30% typically. Again, here in terms of mass, rock and gravel was a big one. Cigarette butts, in terms of volume, were much higher. Obviously, they weigh very little, so in terms of wet weight, they don't really matter. But in terms of volume, there was a substantial portion of cigarette butts at a lot of the sites. And also plastic, not surprisingly. So that's, again, Coke bottles and also pieces of vehicles after automobile accidents. So closing thoughts, observed gross solids or trash in this study was about 70 to 90% by volume vegetation. So it's really could lead to a targeted maintenance type of regime where we really target, if we're going to use catch basin inserts, where we really target right after mowing. That's a time where we know we have to go out and maintain these systems. Gravel, so basically wear of the wearing course, cigarette butts, and plastic were the next 3 most common trash coming off of the roads. The volume on a roughly every 10-day basis was highly variable, from roughly 1/4 of a gallon of trash up to 20, 30 gallons. So there was a high level of variability there. Moving forward, we're really interested in delving further into these data and looking at The contribution of TSS versus trash in terms of the total solids load coming off of the road, and really understanding what are the ecological impacts of TSS versus these sort of larger anthropogenic pieces of trash that are coming off the road, and how does that affect sort of receiving streams and receiving water bodies. So hopefully I've left a few minutes for questions. If not, I have. Okay, fantastic. Are there any, I realize I went through that fast, are there any questions? Yeah.
Probably since there's so much with vegetation, there's no connection to traffic.
That's a good question. So I haven't run the statistics yet. The site that had the most trash on average and the most trash per week was I-70, which is here, and I think it's AADT is something like 120,000 vehicles per day. So I do think that there's some connection. I'm not sure if it's gonna, I haven't run the stats yet. I'm not sure if it's gonna come out in the wash in terms of the statistics, but I do think that, certainly in terms of the litter fraction, if we take out the mowing, I think the litter fraction, it will come out that there is a connection there, yeah. Which I think makes sense. Andy.
At the start of your presentation, you showed an example of how nutrients are a problem in the lakes up above here.
Mm-hmm.
What's your gut feel as to where trash stays?
Like actual litter from.
If you were to catch the trash instead of allowing it to go down into the stream, is that beneficial from a nutrient load reduction standpoint?
I would think that the vegetation component of it would have a lot more nutrients in it than the trash would. And we've done some studies actually for you at NCDOT looking at the component of nutrients in vegetation and leaves, essentially, leaf litter. And it's less than 1% of the nutrients in the aqueous part of the water. And so if I was to spend my money, that wouldn't be the direction I would spend my money in terms of control. Yeah. I know, that's not the answer you want to hear. It's not, that's the easy stuff to control, right? Yeah. The other, all right, are there any further questions? Okay, seeing none, thank you, appreciate it.